Alright, let's now talk about simple regression. The word regression doesn't help most of us figure out what the topic is. What this does, though, is to talk about the estimation of the relationship that we hypothesize between two quantitative variables. Right, variables that we can measure by counting money or size, and we'll call those quantitative variables y and x. In actual fact, we're trying to predict or at least explain the y variable with the help of x. We assume a straight line relationship between the two variables. Okay, and in the long run, what we have in terms of a XY plot is the y variable measured on the vertical axis, the x variable measured on the horizontal, and we will observe a scatter of points from a sample, and we want to fit the best straight line through those points. Alright, to be able to do that, we need to set up some notation. The format for the true or population equation is y is equal to beta sub 0 plus beta sub 1 times x. The x and y we've talked about before. The y is actually called the dependent variable, and the x is called the independent variable. Y depends on x, but x does not depend on y. And sometimes x is called the explanatory variable. Alright, and then we have the betas. Beta 0 is the intercept, or the y-intercept. It's where the straight line cuts the y-axis, and beta 1 is the slope of the equation. And since it's a straight line, the slope is the same everywhere. Okay, so let's draw the diagram, and let's say that our relationship between x and y is something up here. And let's assume that we've started the axis at the origin. Okay, so the point where the the line cuts the y-axis is beta 0. Alright, so there's beta 0 distance between the origin and that point. Slope, go along the x-axis 1 unit, and then you'll go up the y-axis beta 1 units. Okay, so let's now look at an example with this. Alright, so let's look at the equation y is equal to 5 minus 1x. Alright, we're going to draw that line, draw that relationship. What we need is 2 points to draw a straight line, but to help some understanding, perhaps I will use 3 points. So we'll have a column for y and x. In a sense, the x is the input to the system. We'll choose values for x, and the y then will be the output to the system. Alright, so first point, let x equal 0, then y is equal to 5 minus 1 times 0, and that's 5. Next, let's again arbitrarily choose a value, let's say 3, then y is 5 minus 1 times 3, and that's 2. And finally, let's say x is 4, then y is 5 minus 1 times 4, and then y will be equal to 1. Okay, let's now plot those on a diagram. Alright, so here we have an axis, xy axis. Now we can plot these points. So the first point is where x is equal to 0 and y is equal to 5. So x is 0, y is 5, and we have one of our points here. Alright, next point is where x is 3 and y is 2. It's here. And last point where x is 4 and y is 1. It's here. Let's join those. And we can join those points, and we roughly have a line that goes like that. Alright, so remember this is our equation y is equal to 5 minus 1x. 5 is the value that corresponds to the beta 0, the intercept, and that's the value here. Alright, and the slope of minus 1, well, we go along the x-axis 1 unit, and then we will go up the y-axis by minus 1 units. Alright, so the slope is the amount we go up the y-axis when we go along the x-axis by 1 unit. So remember, in this case we started off with a value of y is equal to 2. Alright, then we went to a value of y is equal to 1. So we went down a value as we went from the x of 3 to an x of 4. So we increased along the x-axis by 1 unit, and at the same time we went up the y-axis minus 1 units. So that's our slope of negative 1. In the population, we have a set of points, and let's just have this as a small sample of those points, and a true equation to describe those points. Now, notice that when we draw this, not all the points are on the line. So the distance between an observed point and the true line, or the estimated, the true line, is called an error. And in the population, that error is written as follows: y is equal to beta 0 plus beta 1 x plus Greek letter epsilon for the error. Alright, so the first part of the equation tells us about the straight line. The other part, the plus epsilon, tells us about the true points on or off the line. So the first part is just the line itself. The whole thing is for the actual point. So we're going to go up or down from the line. Alright, let's find for population, but how do we get the sample estimate? So the sample estimate, and we'll sort of back into this, is called a regression. The format that we'll use for the equation for the regression is y hat, hat means estimate, is equal to beta hat 0 plus beta hat 1 times x. Right, so that's the equation to the line itself, the estimated line. An actual point would be y, not y hat, is equal to beta hat 0 plus beta hat 1 x plus the sample estimate of the error e. So this is the true point. Alright, so now we're trying to estimate this equation. So let's say we have the estimated value, the estimated straight line, and it goes through a scatter of points. The distance from any point, any one point to the line, is the error term. We want these errors to be as small as possible, so the straight line goes through the middle of those points. The way we do that and handle our statistics is to first get each of these errors, square them, and add them together. Alright, and this is called the error sum of squares. Alright, what we're going to do is to minimize this quantity with respect to two parameters, beta hat 0 and beta hat 1. And we do that with calculus, and the result is